Okay, so welcome back. We're going to be doing this problem from lesson 5.8. We are in the land of um, proofs. And so if you're feeling a little uncomfortable with what you do and don't understand in terms of proofs, you're in a good place, right? The reason why you're in a good place is because this is like relatively the second day of proofs for our class, and then that means that you should feel uncomfortable, meaning it shouldn't make sense all the time or the first time, but it should make more sense at the end of today than it did at the end of our last class. So this very first problem, I let you guys start already, but it says parallelogram conjectures and proofs. So a parallelogram just means a four-sided shape where the opposite sides are parallel. That's all a parallelogram is. There's other things that you get once you know it's a parallelogram, but that's it. That's the definition of a parallelogram. Opposite sides being parallel. So here it says, what's wrong with this proof? So given that the quadrilateral ABCD is a parallelogram, so the moment that I see that ABCD is a parallelogram, I go in and I make markings. And the first marking that I'm going to make for this guy is that he is parallel. So BC is parallel to AD. And so all I do is I make a tiny little arrow mark like that. And then I do the same thing for A, B, and C, D, except for because I used one arrow, that means I'm going to have to do two arrows here, meaning everybody who has two arrows is parallel to everybody else who has two arrows. Okay. So given that it's a parallelogram, done. Prove that BD divides the parallelogram into two congruent triangles. So I'm going to draw a little dotted line here representing BD. And do you think that those two triangles look congruent? So first, you got to kind of convince your mind that what you're walking towards, your mind believes that it is true. Okay. And if you say, yeah, Miss Johnson, I think those two triangles are congruent, good. How would you prove that those two triangles are congruent? Like if we were in real life, right? And I'm holding up two pieces of paper for those of you who are on internet land, you can't see me, haha. But if I wanted to prove that these two pieces of paper were congruent, what would you guys do? What would you do to prove that these two pieces of paper are congruent? Yeah, I would just stack them, right? This is what I would do. You guys can't see because of my background, but I would stack them like this, and then I would check. I'm like, oh yeah, those do look like the same, right? So if I said, hey, are these two congruent? And I'm holding up a pen, a pencil, and a pen. Are these two congruent? And you guys are like, no. That one has an eraser. That one doesn't, right? This one has like a little rubber place for my fingers to hold, and this one doesn't, right? So those aren't congruent. So in the real world, we just pick it up and put them on top of each other. So in the geometry world, you do the same thing, except for now, like you guys said in the chat, yeah, we use reflection rotation to line them up. Okay. Okay, so the very first thing they say is draw a diagonal BD. We did that. BD is congruent to BD because of the reflexive property. Is that true? Do you guys remember the reflexive property? Yeah, the reflexive property is supposed to make you think of the mirror. When you look in the mirror, right, I see my reflection. I see a version of myself, right? Okay, then it says AB is congruent to DC. AB is congruent to DC, and AD is congruent to BC because opposite sides of a parallelogram are congruent. Okay, everybody okay with that? Okay, and then it says all of a sudden, therefore, triangles ABD, and DCB are congruent by side, side, side. Okay. Is there anything here that they jumped to that maybe we have never talked about in this class? What statement here is the newest kid on the block, according to what we've talked about? Have we talked about, let's see, BD being congruent to BD? No. So this is the new kid on the block, okay? So because he's the new kid on the block, this is the part where we kind of need to talk about, okay? It is true. I'm just going to be honest with you. Oh, sorry. I highlighted the wrong guy. It's this guy. It is true that the opposite sides of a parallelogram are congruent. It is true that those two are congruent, but we haven't talked about it. So in a class of geometry, we don't use anything until we've talked about it, if that makes sense. Okay, so someone said, hey, Ms. Johnson, can you explain BD being congruent to itself? Yes, this is true, right? BD is congruent to itself, right? So let's pretend, everyone pick a different number. Everyone pick a completely different number as the length of this side right here. Everyone picked a different number. Very good. I have 7, 6, 21, 35, 42, 2.2. Good. Everyone has different numbers. Good. Okay. So this is the statement that they're saying. Let's say that was whatever number you chose. Okay. I'm going to use the number 10.2 just for fun. Oops. 10.2. And so if BD is congruent to itself, that means that 10.2 is equal to 10.2. Is that true? Is 10.2 equal to 10.2? Everyone's like, yes. Yes, it's true. If 10.2 is congruent to itself, then that means that the length of BD is congruent to itself. Okay. So we're going to be talking about how we know that this is true today. So by the end of today, you're going to be able to use theorems about relationships of angles formed by parallel lines. We've talked about some of them, remember? And a transversal to prove properties of parallelograms. Previously, we made several conjectures about properties of special types of parallelograms, rhombuses, rectangles, and squares. How might we prove our conjectures about parallelograms are true? How can we prove a quadrilateral is a parallelogram if we don't know opposite sides are parallel? That is, what other characteristics might define a parallelogram? Okay, so today, explain how you would locate the center of rotation for the following paragram. What convinces you that that point that you have located is the center of rotation? So what they're asking is this. I'm going to have you pick a point, and I want you to do this in your mind's eye. I want you to pretend that we cut out a parallelogram like this, right? And if you put it on your desk and you spun it around that point, it would land exactly like this, except for your letters were shuffled. Does that make sense? Or if you want to do a complete 360, then you did a complete 360 and A lands right back where A is. So put your finger on your screen. It doesn't matter unless you have a touch screen. Put your finger somewhere on the screen and say, this is where I think the center of rotation is. This is where I think the center of rotation is. Okay, now that you have that point, can you kind of convince yourself why you say that's where it is? Like, now, like, let's say I said, oh, my center of rotation is right here. I don't know. I need to actually draw the point because you guys don't know where I'm pointing. It's not a pointer. It's a. So, like, what if I said, oh, my center of rotation is right here? Would you agree? Like, right here-ish. Would you agree? Yeah, you guys are like, no, Miss Johnson, that's not going to land A back on A. A is going to be, I don't know, somewhere here or maybe here. Or it's not going to land back on A. So what would you tell me? It needs to be more what? Someone said in the middle. Exactly. Right? In the middle of what? But isn't that point inside my parallelogram? And you guys are like, yeah, but it needs to be more like in the middle. How would you describe it? Like what words would you use? Okay. Give me 1 second, guys. So you guys were better at describing this. So I'm just going to tell you, I know it sounds like really silly about describing something that you don't know how yet to describe, but it gives you a stronger understanding of what it is. So for example, like when we're doing this, you guys said the midpoint. That doesn't make sense because there's no such thing as a midpoint of a parallelogram. Right? There's no such thing as a midpoint of a parallelogram. A midpoint can only be a midpoint of a segment. So does anybody see any segments here that we can use the midpoint of or midpoints of? Very good. Someone says BD, Miss Johnson. Oh, the midpoint of BD? Oh, that's interesting. We were just talking about BD, right? So if I found the midpoint of BD somewhere there, I don't know, not for sure. Yeah, someone else said Miss Johnson, or the midpoint of AC, right? Or even where they cross, right? That's going to be a perfect place. So if I spun this thing around 180 degrees, does everybody see how A goes on to C and C goes on to A? Okay, that's what we're looking for. Very good. So previously you have made conjectures about properties of parallelograms based on identifying line symmetry, rotational symmetry. So line symmetry means like I could cut, like, so say, I don't know, think about the letter A. Sorry. Think about the capital letter A. Do you see the line symmetry in the capital letter A? Where does it go? Describe it. Where's the line of symmetry in A? Yeah, in the letter. Where would I draw the line? Like this? Oh, okay. Thank you for telling me. Like this? Would I draw it this way? Good. Down the middle. Like this? Yeah. My line of symmetry would look something like this, right? Because if I folded it along that line, the left half looks like the right half. That's what a line of symmetry is. So that is that. Rotational symmetry looks more like the letter S. What does rotational symmetry mean? Like, look at my letter S. What do you think rotational symmetry means? Rotational symmetry. Yeah, very good. So you can rotate it and it'll land on itself. Does that make sense? So does everybody see if I spun it around this point, this top curve would look like the bottom curve looks like the top curve and it lands on it? Does everybody see that? Good. That's what rotational symmetry is. Okay, really quickly. What kind of rotational symmetry does this triangle have? What type of symmetry does this triangle have? Can you please pretend that this is an equilateral triangle? Can you guys please pretend that this is an equilateral triangle? Does it have line symmetry, like over here in letter A? Yes, good. It actually has three. It has this one, right? It has up and down. It has this one. And it has a third one. So I'm going to undo those so you guys can look it up better. Does it have rotational symmetry? Does this have rotational symmetry? Can I spin it and it'll land on itself? Not back to the original, but to another thing. Like, can I rotate this so that maybe this is cat? Can I rotate this so that T lands on A? A lands on C, C lands on T. Can I rotate this? Yeah, the answer is yes. Very good. So for those of you participating, thank you so much for participating. It helps me a ton, right? It helps me a ton. Okay, moving right along. If you haven't already drawn one or both of the diagonals of the parallelogram, use this diagram to prove the statement. Opposite sides of the parallelogram are congruent. Opposite sides of the parallelogram are congruent. So I'm going to draw one set in. Wait, where'd it go? I'm going to draw BD in. And your job is to prove that AB is congruent to DC and AD is congruent to BC. Okay. So you can use rotational symmetry. You can use line symmetry. You can use any of those things. So do you see it? So if I picked up something, would I be able to spin it so that it matches? Okay, so let me say this again. Let's try line symmetry first. Does A, B, C, D have line symmetry? Can I fold it along this line and the right side looks like the left side? So can I fold it just like I did here? Can I fold this here or here or here and it would end up being the same? Yes or no? Can I fold this here? Yeah, the answer is no. A lot of you said yes. This is interesting, right? So yeah, the answer is no. No, you cannot fold it. Ms. Johnson, why can't you fold this? So can you imagine folding along this line? Do you see how A wouldn't match up with C? Do you see how A would not fold to C? Does that make sense? Do you guys all see that? So, but what you can do is, you guys all said, I think this has rotational symmetry, Miss Johnson. I think I can spin this thing. Okay. And is everybody convinced? Can you spin this thing? Can you spin A so it lands on C? Can you spin A so that it lands on C? Yes. So because we can spin A and it lands on C, so I'm going to pull these apart as triangles. If that helps you better, let's do that. So I'm going to spin the triangle ABD. I'm going to spin it and line it up like you guys said. I'm going to spin it and line it up so that it lands on this triangle here. Can you see that happening? Yes? Okay. So, Ms. Johnson, it seems like a funny proof to do that. Is that always true with a parallelogram? The answer is yes. So because of its rotational symmetry, I can spin triangle ABD, ABD, so that it lands on. Now, who does A match with? Who is A going to line up with? Who is A going to line up with? Yeah, A has to line up with C. Very good. Now continue on with me, right? Who does B line up with? Who does B line up with? Yeah, so when I spin this, right? When I spin this guy here, A goes this way, right? So maybe I draw arrows. I don't know if that'll help you. I'm trying to get you to see something that's not really like there. Does everybody see my A going all the way around to C? So you're right. B has to go land on D. B lands on D, right? And then similarly, I don't know, I need another color. D lands on B. Is everybody good with that? Okay, so now I don't want you to focus on the points. Now I want you to focus on the sides. Okay, so look at this side here. When I take AB and I rotate it all the way around, right? Who does it land on? Who does AB land on? Yeah, very good. Okay, so some of you are very visual learners because you're like, I totally get this. I totally get this. Exactly. So you see that it lands on that. Does everybody see that? Now, when it lands on that, is there any extra pieces like hanging off, or is it fit exactly right? Does it fit exactly right? Yeah, it fits perfectly. Okay, similarly, let's look at this guy. when I spin the side AD, when I spin side AD, who does AD land on? Who does AD land on? Oh, you can check it. Hold on. Give me that. Who does that land on? Who does AD land on? Yes, very good. It lands all the way, it goes all the way around. So maybe I do this like arrow like this, right? Maybe that'll help you guys see it. So not only do points rotate all the way around, but so can things. Okay, so someone says, because when A lands on C and D lands on B, the side AD will land on the side BC. Is everybody okay with that? Okay, so therefore, you guys just use rotational symmetry to prove that the opposite sides are congruent in a parallelogram. So that means you can use that in your proof. So I'm going to add this to our little list here. It's not a little list anymore. But you said, so definition of parallelogram. So parallelogram definition, opposite sides are congruent. And so we also have in a parallelogram, opposite sides are, I said this wrong. Look at, I wrote it wrong. The definition is when they're parallel. Does that make sense? So now you can use this. So the moment that I tell you, hey, we're dealing with a parallelogram, right? The moment that I say, hey, we're dealing with a parallelogram, you have opposite sides are parallel, you have opposite sides are congruent. Okay? Is everybody comfortable with that? So now we're going to move on to the next one, and I'm going to have you guys kind of think about this one on your own. So it says, if you haven't already, draw one or both of the diagonals of the parallelogram. Use this diagram to prove that opposite angles of a parallelogram are congruent. So I want you to look at this, and I kind of want you to think about what we did here, and I want you to think, does that still work? So I'm going to pause the video. I want you to think about, could opposite angles of a parallelogram be congruent? Really quickly, are you comfortable with the term opposite angles? Who are opposite angles in this case? Who are opposite angles? Who would be the opposite angles in this case? Very good. A and C and B and D. So they're asking, is A congruent to C and is B congruent to D? Is that okay? Okay, so I'm going to pause this really quick. You guys are going to come up with it. If you're done with this one, move on to the next one. But I really want to see if you guys can do this. Okay, so this next part, it says opposite angles of a parallelogram are congruent. Yes, very good. Someone said it's almost like the stuff from before, because if you flip them or rotate them, it'll match. So just like side AD rotated all the way around to get to BC, if I take angle A, not just point A, but if I take this angle, I don't know, I'm going to do something like this. If I take this angle and rotate it here, does everybody see how that works like that? Yeah, right? And same thing goes with this other angle. Maybe I should have used a different color. Hold on, let's use a different color. So notice here I'm using two little arc marks to denote the difference between angle B and angle C. You'll see them come up in a second. And then when I rotate that around, I agree. So let's see. Oh, it's taking a while to show up. Hold on a second. All right. Can you imagine that I drew another angle like this? Okay. So now I want to copy this down, that opposite angles of a parallelogram are congruent. So I want to copy that into our definitions. So opposite angles of a parallelogram are congruent. So wait, Miss Johnson, the moment that I know it's a parallelogram, I get all three of these. Actually, there's one more. You actually get this one too, that the diagonals of a parallelogram bisect each other. What does that mean? What does bisect mean? Do you guys remember that word bisect from before? What does that mean? Bisect. If you break that word down, it makes sense. Yes. Good. They cut each other in half. Say what, Miss Johnson? I'm just going to use this as M because I don't know what else to use it. Can you imagine? So what it means is, remember how you were saying I need, like up here, you guys said, Miss Johnson, in order to do that, all you have to do is find the midpoint. This one where we were rotating it. If you find the midpoint, Miss Johnson, you can rotate it. So actually you were right in calling it a midpoint because it's the midpoint of both diagonals, right? It's the midpoint of both diagonals. So yes, you are right. And the way you can do this again is you rotating this, if you rotated CM all the way around, can you see this? Can you see this rotating all the way around and hitting right there? This section here goes to this section here. Do you guys all see that? Do you see how it's the same? Yeah, very good. Okay, so I'm just going to add this one little thing to this. And let's see. Diagonals of a parallelogram bisect each other. Okay, diagonals of a parallelogram bisect each other. So wait, Miss Johnson, you get all of these things when it's a parallelogram? Yes, you get all of these things. It's almost like a combo, right? Like when you order, I know I'm thinking of In-N-Out right now. I don't know why I'm thinking about In-N-Out, but if I say combo number one, wait, no, combo number two. If I say combo number two, that means I get a cheeseburger, fries, and a drink, right? So I don't have to say, can I have a cheeseburger? Can I also have fries? And can I have a lemonade? By me saying number two, I get all of those things. Now their questions are, do you want grilled onions? I say yes. And then she's like, what kind of drink would you like? Actually, she just hands me a cup because then I fill it up myself, right? So it's almost like a combo. Like the moment that I get a parallelogram, I get opposite sides parallel. I get opposite sides are congruent. I get opposite angles are congruent. And I get diagonals that bisect each other. Okay. So I kind of wanted to go over your, let me find it, your takeaways, and then we'll call it a day. And then you guys are going to start your homework. Remember, we like doing this. Okay. So hold on. Let me go grab my takeaways. Okay. So today we formally proved the theorems about parallelograms. What three things did we prove? In the chat, please. In the chat. I want three things that we proved. I am going to type them here. What three things did we prove? Jonathan, did we really prove them? Yeah, because we used rotational symmetry. Yeah, but what did we learn about parallelograms? It was the three things that I typed onto our definitions and theorems page. Right? Very good. Very good. So number one, we did opposite sides are congruent. Exactly. Good job. Okay. Number one, opposite sides are congruent. Done. Okay. So the moment that I tell you it's a parallelogram, boom, it's that combo. I get all three things. Technically four because it's the definition. Very good. Oh, someone gave me all of them. Okay. The second one we got was opposite angles are congruent. Good. What was the last one? What was the last one? Sorry, I'm trying to give you guys participation. Yes, very good. Diagonals bisect each other. Okay. So to be technical, I would always want you to put of a parallelogram. So I'm going to write that in here as well because I like when you guys are very, very specific. So of a parallelogram are congruent, opposite angles of a parallelogram congruent and diagonals bisect each other, so of a parallelogram. Ms. Jonathan, why did you have to write that? You don't have to write it. I'm going to just tell you right now that on the test, if you see this, I saw some of your messages. Yes. So yes, I saw some of them. Yes, ma'am. Yes, yes, yes. So Ms. Johnson, if I forget to say of a parallelogram, are you going to take points off? No. But I will push you to write it correctly, because the more, this is a practice in you communicating really clearly. So when you say opposite sides are congruent, I probably will write you a note of what opposite sides of what, and then you'll be like, oh, a parallelogram, not a big deal. I know what you're talking about. But for you to practice how to be very clear is a really good practice. Okay. Second takeaway. We also considered some ways how to show that a quadrilateral is a parallelogram by using the converse statements. So do you guys remember what converse means? What does this word converse mean? Do you guys remember what I told you converse means? Yay, switch. Very good. So I need you guys to imagine that your Converse shoes are switched. Your left shoe is on your right foot and your right shoe is on your left foot. Feels funny, right? So we're going to switch these statements. And so you're like, Miss Johnson, how do you switch these statements? So if before we said opposite sides of a parallelogram are congruent, we're going to take the parallelogram and put it at the end. We can kind of say something like this. If opposite sides are congruent, then it's a parallelogram. Okay. Does that make sense? So I'm going to write this for you. I'm going to write the first one for you. And you guys are going to try to write the second one. And I'll be pretty loose in this one. If opposite sides are congruent, then it is a parallelogram. So before we had, because it's a parallelogram, I know the opposite sides are congruent. So now I'm going to switch them because I know the opposite sides are congruent. Now I know it's a parallelogram. To be really honest, this is not mathematically sound. I will show you what words are missing, or maybe you can figure it out, right? So can you try writing the other two? The other two have to do with the angles and the diagonals. So I'm going to give you a couple seconds to do that. So these are done. Got two people. So I got two people who wrote down, and I wish I could snip it and copy it into here. Oh, I can. Hold on. Can I copy this? I'm literally copying and pasting from your classmate here. Look at it, it works. If opposite angles are congruent, then it is a parallelogram. I'm going to change that question to a statement. That is perfect. Good. So I'm going to fix what's wrong with this. If opposite sides of what is the only phrase that I'm looking for. And so you don't want to use the word of a parallelogram, because then it's a parallelogram. So if opposite sides of a quadrilateral, and the reason why we're using a quadrilateral is I need it to be in the family of four sides, right? So I'm going to take this phrase again, add it here. And then we're good now, right? So what is the last statement? So how would you construct the last statement about diagonals? How would you construct the last statement about diagonals? If what, then what? If what, then what? So let me say, oh, I don't even want to type that. So go ahead and try that. So if what? Yeah. Good job. Okay, I'm going to copy. Oh my gosh, I didn't realize that I can copy and paste from the chat. I'm so excited right now because look, boom. So excited. Okay. So let me give credit where credit is due. Exactly. So if diagonals, I think you just put an extra A in there for fun. I like extra A's as well. If diagonals of a she even put if diagonals of a quadrilateral, I would take this part out and put bisect each other. Bisect each other, then it is a parallelogram. Parallelogram. Okay. I still spelled this wrong. Dang. Diagonals. Diagonals. Is that right? Yay. Okay. So here you go. This is how you do it. Miss Johnson, why is it important that we went forwards here and then we did the converse here? Because if I give you a shape and I say, hey, look, both sets of opposite sides are congruent, then you know it's got to be a parallelogram or someone in his family, right? Okay, last one here. So we use both definitions of rigid transformations and triangle congruence criteria in our proofs, as well as postulates or theorems about parallel lines. So rigid transformations are really important when we're trying to prove stuff, right? For example, what, Miss Johnson? That we can show triangles are congruent, right? Triangle congruence criteria are most useful when what? When we're when so once we have triangles congruent, the very next line is always going to be like using the parts of those triangles because now they're congruent, right? The last one says parallel postulates and theorems about relationships among angles formed by parallel lines and a transversal are most useful when we're given parallel lines and a transversal, and we can make claims about all those angles. Okay, so Ms. Johnson, what is this about? Like, why did you give us this? So it's going to help us understand like when to use what, and it should be really like shaky right now. It shouldn't be like, oh, I know exactly when to use rigid transformations, Ms. Johnson, it's this. It should still feel shaky. Okay. So if you understood today, this was the biggest takeaway. Slide 11 and slide 12. So Ms. Johnson, what if I still don't see what you see in terms of rotation and stuff? That's okay. Just keep practicing.